All right, so just a couple more videos related to text mining. We're going to look in this video at Zipfs law. So Zipfs law is based in linguistics. And so what we're looking at here is how efficient is our communication. The idea is that efficient communication has the most common words appearing twice as often as the second most common words, and then 3 times as the third, and so on. So what we should see if we order the words by frequency is that it should drop quite quickly. And if communication is not in alignment with Zipf's law, then it's considered to be redundant, long-winded, circular. It's not efficient, it doesn't get quickly to the point. One interesting component is that Zipf, who did this original work, discovered this relationship by manually counting all 260,430 words in Ulysses by James Joyce. And this comment was, the magnitude of words tends on the whole to stand in an inverse, not necessarily proportionate, relationship to the number of occurrences. So of course, we're not going to count these words by hand. We can have a computer do it. But if you are looking at speech, for example, or you're looking at policy documents, is your arguments the most concise, the most efficient in terms of the way it's worded? So we can take our text and we can actually run Zipf's law and do a comparison to see who is more efficient in getting across their message. So to do this, let's just get out of here and go to our text. Okay. So in our videos, we've been looking at this document about AI from Canada, and a document about AI from the US, and a document about AI from the European Union. So we have imported in previous videos, we have scraped the PDF and pulled it in, and then we built a pre-processing pipeline where we could clean it up. So based on that, we have what looks like this, okay? Now, notice we have some numbers that are still appearing in this. It hasn't been tokenized. It has all of the weird symbols that are gone, but we need to get rid of all the punctuation, and we need to get rid of all of any type of weird spacings. So what we're going to do is we're going to apply some additional cleaning to it. We had left, for example, punctuation before because we were then going to do our sentence tokenization, which then left the punctuation to help with the tokenization process. But in this case, we're going to remove any numbers and any extra punctuation from this. Okay, so let's run this little function here. And all this is doing is make sure you've imported RE for this to work. If you didn't do the previous video that did the first cleaning, well, one, you need to, because otherwise you can't get it to here. We import the package RE. So if you want to run this code, just a reminder, drstephpowers.github.io/BIA, and we're here in text mining, and then you can run through the code. All right, so here we have AI can. We're going to import RE. We're going to run this new function here where we're going to sub for a bunch of these symbols, just empty space, and apply that to our text. So let's do that to our AI can. And you can see now, for example, that the numbers are gone, that 1 of 27, that 1031 has disappeared. We've still left the periods at the end of sentences that isn't here in the symbols at this time. So we still have the ends of the sentences in case we want to do some sentence tokenization later. But first, we're just going to remove the numbers. All right. So now that we have this, what we can do is we can use count vectorizer, and we are going to, from sklearn.feature_extraction.text, import count vectorizer. And we are going to take from skippy.interpolate, we're going to import make interp spline. So we're going to create some splines here as we're trying to do some graphing to show our Zipf's law. You'll also need pandas. We're going to plot, so we need matplotlib.pyplot as PLT and numpy as NP. All right, so we're going to take our AI can, we're going to turn it into a list here. We'll call this corpus AI can, and we will do our n-grams here. So let's just deal with just bigrams and then our unigrams. So this is the same function we saw in the previous video. If you, as we talked about before, remember it goes up to but not including. So if you want to be able to write this as give me unigrams and bigrams, so you want to write it this way, you need to amend the code to be +1 here so that this can be unigrams and bigrams. Otherwise, recognize it's up to but not including if you don't have this. All right, empty table or empty list. This is going to create our frequency table that is going to combine both the unigrams and the bigrams. So we're going to pull this here. Okay. Now, in this case, we are going just the unigrams and the bigrams. So if we ran this here, we get nothing. That's because we don't have the trigrams in this location. What we have is that the 0 location is the unigrams. There you go. The 1 location is the bigrams. If we had made this 1 to 3, then the second location is the trigrams. So if we do, oh, here, this is what I built from the previous one. All right, so let's make this. Let's go to 3. Okay. So if we go to 3, and you can see now here are the trigrams. Clear it, then run it, then do it, and then it doesn't give you weird crap. All right, here's the trigrams. Use generative AI, guide using generative, so on, right? Okay, so we could build this and say new bigrams, and it's going to take anything that is in the trigram, and then it is, if it appears in the trigram, then we're going to not have it as part of the bigrams. That's what we saw we were doing in that previous video. Okay. And then we can do the same thing here, and we can say if it's in the bigram. If it's in the bigram, then don't include it in the unigram. We're going to have that same issue we had in the last video, which is we're going to remove it for the bigrams, and then it's going to appear again in the unigrams. So you can clean that up. So this is the same kind of command codes we were using previously. All right, so what we've done is we now have a list of trigrams, bigrams, unigrams, and we have created a table here. Here's our words, here's our frequency counts. So whether you're doing this with unigrams and bigrams and trigrams combined, or whether you're just going to do just the unigrams, you can do this here. We've combined them, and the reason we've combined them is because there's often words that are together. Those two words are a proper noun. Okay, so if we're looking at this here, to check our Zipfs law, what we do is call Zipfs law says that the efficient communication has the most common word appearing twice as often, the second most common it's 3 times as much as the third, and so on. So it should be dropping quite quickly. And so we're going to plot this. We're going to plot the word and the frequency, and we're doing this for the AI can because we'll do a comparison. And so we get something that looks like this. To know whether or not it matches the distribution that Zipfs law says it should, then what we can do is we can use this smoothify and a Zipfian curve value to adjust it. So what we're going to do is we're going to reset the index. We're going to create a function that is going to go from the range of 0 to the length of the top word list. And it is going to then use those splines here to smooth out and show what it should look like. So I'm going to create a smooth curve is what this is doing. Okay. So given the information here, if we took this and turned it into a smooth curve, then matched Zipf's law, then that's the Zipfian curve value that's pulling from our data set here. So it's taking it, figuring out what the Zipfian curve should be, and then smoothing it. Okay, so that's what all these commands are doing here. And then we're going to turn it into percentages rather than counts. So if we replot this here, what you get is you get the orange is Zipf's law, and then the blue is the original data. So if we gone back, that's the original data. What we're doing with all this code here is we're saying, okay, given the original data, if we had used Zipf's law, which is that in that relationship that says it should be decreasing at a particular rate, and we smooth it out, that's the smoothify, then it should be what you see here in orange, and what we see here is the blue. So what we can do is we can run this with the US data, with the EU data, and see which particular country is more efficient in discussing a generative AI. So we could do this again, but with the US or the EU. So pause the video, give it a try, see if you can't come up with what that looks like. And we could look at, I'm actually going to take this down. So let's just take this down to just the bigrams. And I'm just going to rerun this quick here, and we can see if it looks any different. This, of course, is going to error because there is no trigrams at this point. And because there are no trigrams at this point, I wouldn't run this line of code here. I would only run this one to create my table that has just the bigrams and the unigrams. So you can see we got rid of AI and generative to create these. Once you get the trigrams, it's kind of too complicated. All right, so let's just do unigrams and bigrams. Here's what our graph looks like. And then we're going to compare it to Zipf's law. So it's going to take that same data and it is going to look at what it should be if it followed Zipf's law. And it will then compare it to, and you can see once I take out those trigrams and I just look at unigrams and bigrams, we're much closer to Zipf's law. So let's repeat that process, and let's do that with, let's do it with the EU. So I'm going to do here, let's do AI EU, AI EU. Okay, we have those from previous. Create this empty. All right, this function hasn't changed. You don't technically need to rerun it, but we're going to do bigrams and unigrams. Okay, so I'm changing this to the EU. There's no trigram, so I'm going to skip this line and I'm going to skip this line. I'm going to have the bigrams take out the unigrams that match. Run, run, run. I'm going to call this AI EU. And so I can then have it give me, just as a comparison, top WF underscore AIUU dot head, so that you can see the comparator here. So with the EU one, EU Europe risk requirements, AI systems appear most frequently, whereas the Canadian one, it was generative AI and federal institutions. This plot here was the AI can. I'm just going to trade this out for below it. I am going to say, okay, show me AI EU. AI EU. AI EU. And let's call it AI EU. Okay, show me that plot. So here you can see this one. In order to get Zipf's law, AI EU. Okay, we just reset the index. You don't have to rerun this function because it's already here, but what you do have to do is trade it out so it's not the Canadian one. This is the EU one where it's going to find what the equivalent would be under Zipf. and then it's going to smooth it using that smoothify function. That's this here. And then we can get the frequency percentages. So I'm just changing this out to EU and EU. So I can turn it into probabilities here. And then I can create a new plot. I'm going to leave this one as is so I can toggle back and forth. But I'm going to add some code here. And I'm going to make this one EU. Frequency and AIEU. Okay. Plot. Okay, so this was Canada as a comparator. This one is the EU. Notice how it's way less concise, way less efficient in its wording. We notice the EU document is much longer than the Canadian one. The Canadian one's quite short, and so the language is also very efficient in terms of it matches that Zipfs law, which says that efficient communication has the most common word appearing twice as often as the second, 3 times as the third, and so on. So we can compare these documents and we can see the European Union document is much less efficient in its communication, much more secular and repetitive than the Canadian one. So I encourage you to try the US one, write the third graph, and see what you can find.